And Bill, why don't you take it away?
Okay, great. So thanks everyone for coming. Welcome to our kickoff symposium for the new DOE consortium. Thanks for attending. We'll start with the first of what will be two quantum information talks, one today and one tomorrow. The first one will be given by Peter McMahon from Cornell, who will tell us about near-term hardware and applications. Peter.
Great, thank you very much. Let's see if this is working. So does this show up showing the full slide?
Yes.
Okay, wonderful. We'll call it good then. So thanks very much for the introduction, and thank you very much for the invitation to speak. I feel a little bit fish out of water and a little weird about being the very first person in the this new set of series of talks, being probably the most QISy of the QISy people, so probably the furthest away from HEP. But nevertheless, here I am. And so when Bill asked me to speak, I told him that my kind of probably the thing that I would be most comfortable and maybe most useful for me to try to describe to this audience is what is the state of the art in quantum computing hardware, especially things that are available commercially, but also to whatever extent is state of the art in academic labs, also in academic labs. And so essentially, what are the constraints that the state of the art now and in the near future place on what experiments we can imagine running that are related to high energy physics or gravity, etc. So this is going to be in some sense, a very practical talk about the practical realities of the hardware that exists now and will hopefully exist soon. So before I kind of dive into the material, this is kind of both a little bit of FYI of who's at Cornell, but also some acknowledgements. Of course, our work has been funded by this consortium and the previous rendition of it from the DOE. And the material that I give in the talk today, to whatever extent it mentions things from HEP, everything I've learned is from these three people here, Tom, Paul, and Elliot. Tom and Paul are faculty in the physics department, and Elliot is a PhD student who's co-advised by myself and Paul, and is straddling the high energy and QIS worlds enabled by this grant. And so everything I say about HEP is everything I've learned is from them. Everything I get wrong is, of course, my fault. And like I mentioned at the caveat at the bottom of the slide, there are certainly other people at Cornell who are interested in this crossover, but this is the set of people that I've been interacting with mostly on this topic since I started at Cornell about 2 years ago. So the grand plan for today is to try roughly touch on these four sort of topics or points. The first is to explain what are the sort of constraints that hardware limitations in practice place on experiments that we can run on them. And connected with that, what is the landscape of hardware, quantum hardware that's available today, and what we can expect to become available over the next couple of years. So what are the constraints that will be placed on experiments we can imagine running in the near future? And given this, what are the sort of properties or features of experiments or applications that we should look for if we would like to run experiments in the lab? And like I said, this could either be on commercial machines, but also we could imagine building custom machines or using fairly special purpose machines that exist in academic labs. And then I've also included something of a brief survey of the largest experiments that I know of that have been run on quantum machines to date that I think would be perhaps interesting to this audience because they sit in the land of either quantum simulation or sort of more fundamental quantum dynamics experiments. So that's the goal. And as was said in the introduction, I absolutely welcome interruptions and questions as we go along. I think we have an hour-long slot, and I don't know that I have enough slides to go for a full hour without questions. So you absolutely won't be disturbing somehow the total amount of material. I can tell you if you ask questions when it makes sense to in the middle. So please do feel free to interrupt. So what are the challenges for practically realizing experiments of quantum circuits or quantum simulations on machines that are available right now? So perhaps the first and most obvious limitation is that we have a relatively limited number of qubits that are available to us in current experiments. Depending on which piece of hardware, which experiment, typically the number is somewhere between 20 and 50, at least if one is looking for well-controlled, low decoherence qubits. The second is that even in the case of the best experiments that have the lowest noise and the lowest errors of decoherence, there's still a very finite amount of noise or decoherence. And this limits the maximum circuit depth one can run in a quantum circuit model sense, or in an analog quantum simulator sense where you're just time evolving some Hamiltonian. This limits the maximum amount of time you can evolve the Hamiltonian for before, well, everything has become decoherent and it's no longer meaningfully quantum. The third major practical constraint is that in many machines, there is a limitation on the connectivity between the qubits in the system. And this is typically something that's, the connectivity ends up being local. Often quantum machines are constructed almost in a 2D plane, or you can approximate it as devices as being planar. And so you end up with connectivity like 2D square grids. And as an example of this, on the right-hand side, we see connectivity of Google's Sycamore chip, where each of the squares here is a qubit, and there are nearest neighbor interactions on this rotated square, mediated by other couplers. But the upshot is that the qubits talk on this square lattice, and this ties in heavily with the maximum circuit depth, because in a circuit model, you can of course swap gates to mediate interactions between qubits that are far apart by swapping information between the ones that are between them. But given that you have a finite circuit depth you can execute, this now limits overall what you can do. And then
I have a question.
Sure.
Yeah, sorry. Do you have a rough scale, say, of this time scale or circuit depths?
Sure. So typically the deepest circuits that people have been executing and getting meaningful results back, so it's before things have decohered so much that it's no longer sensible, people are typically running circuit depths of, let's say, of order 50 gates. And it's normally the 2-qubit gate fidelity that is limiting. So people could run much deeper circuits if they only use single qubit gates, but those are not entangling and don't propagate information. So 2-qubit gates are what people normally are counting in this depth of somewhere between 20 and 50 operations.
Mm-hmm. Yeah, and in our paper we were able to get to about 25 ansatz layers, where each ansatz layer was like 2-qubit gates between all of the adjacent qubits.
Mm-hmm.
Right. The paper Elliot's referring to is some work we've done on variational quantum algorithms. We were running on IBM's machine, which has error rates that are a bit higher than Google's. That's why we were probably constrained to a little bit lower depths than what had been achieved in some of the other machines that are available.
Mm-hmm. Yeah, okay,
and then a fourth, kind of also very intuitive constraint is that you are limited in how fast the operations are, which is somehow less important than the first three constraints, but is also still, it ends up being practically important, because there's a strong sense in which, well, the gate operations, they tie into what circuit depth you can achieve, because you have some decoherence time for your qubits, and the gates take a certain amount of time, so there's a certain amount of decoherence that happens during the gate operation, so that goes into the calculation of what your maximum circuit depth is. But there's an additional impact of having low gate speeds is that if you would like to repeat the experiment tens of thousands or hundreds of thousands of times because you would like to variationally modify parameters in the circuit, then you start actually going up against the limit of what is practical to do of it. You're starting to take hours to days to weeks of compute time to perform your sort of many hundreds of thousands of executions of the circuit. So this operation time, even though it's somehow not as important as the first three things, is actually an important practical limitation.
Oh. Also, another comment about number 2, the circuit depth. People might be used to thinking of like circuit depth in terms of number of Trotter steps if you were to think about discretized Trotterized time evolution. And of course, the number of Trotter steps that you can run depends on the Hamiltonian and the number of qubits, etc. But if you have like a relatively simple Hamiltonian that's like a 1D spin chain, you can get like at most like 10 Trotter steps. So we're not talking about like really deep circuits here.
Right. And there'll be a little bit of material later on kind of what is the most people have achieved so far in quantum dynamics simulations that touches on this. So given those constraints, kind of there's a number of metrics you could think about using to quantify how good some given piece of quantum computing hardware is. So the number of qubits, the maximum circuit depth you can achieve, the connectivity of the qubits, which ties into the maximum circuit depth, and operation speed, which likewise. And these are some numbers that I'll properties, and some in cases numbers that I will show for hardware coming up. Something to mention that sometimes comes up in the QIS world that I want to let you know that it exists in case you see it, is that people would like a metric of how good a piece of quantum computing hardware is that doesn't involve having to stare at 4 numbers or 4 metrics. So there's been this introduction of a metric so-called quantum volume, which is a single number that is a metric that was proposed by IBM that tries to sort of bake together all of 1, 2, and 3. And it doesn't incorporate speed, but it does try to capture the meaningful aspect of how many qubits, what circuit depth, and what connectivity you have. So you'll sometimes see people talk about quantum volume, and that's how that relates to these more sort of fundamental metrics. And then the speed is also very important, even though in practice, even though it's not included in quantum volume. But this is actually something now that people have started to define metrics to make this something that you can kind of compare across different machines more easily as well. For example, there's this recent paper from IBM giving their definition of what a good metric for speed is. So those metrics, there are, at this point, besides all the academic groups working in quantum computing, of which there are a vast number, there are a very large number of hardware players in the commercial world. And as an experimentalist, I'm still building experiments and so on, but I'm sort of fully aware that for people who are more on the theory side and would like to just come up with some algorithm or simulation that they want to do, and they want to just run it, that the commercial hardware players are providing an opportunity that was previously much more difficult to achieve before they were commercial players, which was previously you would have to partner with some experimental group into some collaboration, and the hardware and academic groups tended not to be very easily programmable and so on, because it's all sort of done by graduate students who are not optimizing for ease of use and so on. But now with commercial players, you can come up with some simulation you would like to do, and as a theorist, use it almost as if you would use a laptop. You can program in Python and run your desired circuit or algorithm on some commercial piece of hardware. And this is a sampling of the players across various technology types. There's many different players working in building superconducting circuit machines, quite a number of players building trapped ion machines. There's also a rising interest in a number of companies now exploring arrays of neutral atoms. There's a few companies exploring photonics, there's still a long-standing interest in spin qubits that are somehow less mature than the others, but nevertheless a lot of effort there. And then there's also quite a lot of news, maybe less actual sort of practical developments in topological quantum computing as well.
Peter,
this is kind of some snapshot of the landscape. So go ahead.
I have a comment and a question. My comment is that I don't know if you know the bottom of your slide is cut off. I don't know how
let's see if I can fix that. I did not know that, but maybe if I stop sharing and I share again, it will fix that problem, or maybe not. Let's see.
It's probably not that crucial, but your footnote was not legible.
Okay, how about now?
Same.
Let's see. Okay, let's do one more rendition of this. Sorry about this. It's not, the footnote's obviously not crucial, but yeah, Windows is deciding that it wants to put the taskbar there today, and it's just not, it's not going away. So we'll have to forfeit the footnotes.
Yeah, if it's something important, you'll just tell us.
Sure. Mostly there are caveats about like not angering people of like, yep, this is not the full list.
Right. Is spins, is that like diamond NV centers, or what is spins?
Right, yeah, so spins in solid state systems like diamond count as part of that, but also in particular, these three companies here tend to be working on gate defined quantum dots, where you have some 2D electron gas and you deposit some metal electrodes on top, and you can confine via Coulomb potential a single electron within this artificial quantum dot, and that electron spin is your qubit.
I see.
And this is an approach that people really like for the sort of future promise, in the sense of it's very either directly CMOS compatible or very close to the kinds of things Intel already makes. So there's this sort of hope that if you can make it work really well with 10 qubits, let's say, then you can scale it much more easily than other approaches. That's at least the story. Whether it works out that way is a different matter.
And is it room temperature?
The gate-defined quantum dot ones that Intel and HRL, for example, are pursuing tend to be at dilution refrigerated temperatures. So same as superconducting circuits.
I see. Okay.
The NV centers can operate at somewhat higher temperatures, or they're generally, the experiments there are still done at liquid helium temperatures, just not Dilfridge temperatures. So this is some snapshot. Sorry, did you have any other question, or was that it?
That was it. Thank you.
Okay, great. So this is some snapshot of kind of various names you might see when people are talking about hardware players, but let's kind of dive into a subset of these that actually have machines that are either available already or should be available soon that we can imagine using. And some of these machines are ones that we've at Cornell already been using via cloud access. And what numbers people have hit in these metrics that I was talking about earlier. So these are kind of pretty raw numbers that I haven't tried to translate to what do they mean for applications. So you can see in the column of number of qubits, there's some fairly large variation in how many qubits people have. And an important thing to note about this is that while larger is better, kind of in isolation, to think about how useful a quantum machine is to you and your application, you need to consider the other metrics too. So IBM, in some sense, are nominally ahead of Google, and they have a 65 qubit machine that they've fielded, whereas Google's is up to sort of mid 50s. But that doesn't mean that the IBM machine is better or more useful for some application than Google's, because you also need to consider the connectivity and the 2-qubit gate fidelities and speeds and so on. And of course, the same story applies to the other systems that we see. So across superconducting circuits and trapped ions, there's relatively comparable numbers of qubits.
Peter, I have a question. Did you have a question, Veronica?
Oh, sorry. I just wanted to check. So on this type of what would be the quantum volume? What sorts of numbers would the quantum volume be for these?
That's a good question. I feel like the quantum volumes, let's see, what are what do they work out to be? The quantum volume is kind of a funny metric because it goes exponentially. I feel like IonQ have said that they have a quantum volume in maybe the millions, whereas IBM is quantum volume of maybe in the thousands, I want to say. Don't quote me on that, but something like this.
It's most easy if you simply quote the log of what they quote, because that's
exactly
the sort of physically relevant thing, right?
That's right. Although then some companies will quote not the log and some will quote the log, so it gets a little confusing. I think the main thing I'll say about quantum volume is the metric exists, but when someone quotes it, you need to look very carefully at whether exactly what number they're giving you. Are they giving you the log of it? Are they giving you it? And compare it in an even fashion to whichever other number you see.
Oh,
In the chat, somebody said it's 7 for IBM.
well, I'm on the IBM website now. They list the quantum volumes for their devices. So IBM Montreal has a quantum volume of 128. That looks like the highest one out of all of these. Oh, yep. You can, I don't know if I can show you.
Yeah, that corresponds to 7 good qubits that you can do depth 7 on.
Right.
Out of the 65, or?
That's correct.
Okay.
So this is why the 65 is kind of a number. You can see it's true that they have a system with 65 qubits, but in some sense, how many of those are practically usable? The number is much less.
Oh, their 65 qubit devices have quantum volumes of 32. It was a
5 qubits.
27 qubit device has a quantum volume of 128. Anyway.
And a big part of why the 65 goes down to sort of a much smaller number that's practically usable is both the connectivity. IBM systems tend to have these kind of topologies where they just have 1D connectivity, but the quantum volume metric bakes in that you may want to interact all the qubits with all the other qubits. And there's also a 2-qubit gate fidelity that's in some sense good. It's 98%, but it's 98% is still not that great. We want more. And I will show some examples later, or list some examples later of people doing actual applications, because no matter what metric one looks at of like the number of qubits and connectivity and 2-qubit gate fidelities, or whether you do something that's a little bit more single number metric like quantum volume, it's still not telling you the full story. What you really want to know is, can you run the application you want it to run, and how many qubits could you meaningfully do that on? And nobody has a single number metric that's good for that. And just like in classical computing, almost every metric can be gamed in some way. You ultimately care about the performance on your particular application. So some other things to note here. One are that as far as number of qubits goes, we're in the sort of tens with superconducting circuits and trapped ions. So that's kind of a target for if we want to design applications to run. We should be, for the near term, for these systems at least, be targeting sort of tens of qubits. That said, the neutral atom systems seem to be able to scale to larger sizes, although we'll see how that works out in practice once one builds a full quantum computing system out of it. But in some sort of early demonstrations in the academic groups that are the precursors of these companies at Harvard and the Institut d'Optique, they've generated lattices of about 200 atoms. And so there's some prospect that maybe we'll have sort of 100 plus qubits available from these companies in the not too distant future, but we'll see. These are still, they're in brackets because they're not commercial devices yet, and they're not fully operating quantum computers yet in some sense either. Connectivity is also very important. Here, superconducting circuits at best tend to have 2D square or other kind of 2D lattice connectivity. Although not all the companies manage to achieve that, there are also ones that are only 1D, 2D being better than 1D. And the neutral atom is also very naturally done in 2D. There's also some academic work on 3D. Whether that gets translated to commercial devices is still to be seen. And in trapped ions, up until at least sort of 50 qubits and maybe beyond, we can expect there to be all-to-all connectivity for the trapped ion machines. And so this is a strong advantage of them, that they have this all-to-all connectivity capability, whereas the other leading approaches at the moment don't. The 2-qubit gate fidelity is generally the limiting fidelity in these systems. And in this sense, in this metric, most of these systems have at least comparable maximum reported 2-qubit gate fidelities when you are building it in a system where there's more than just 2 qubits in total. For example, Google has demonstrated 99.4% average fidelity, and there's a demonstration from Honeywell of 99.5. The neutral atoms are maybe a little bit lower. It's still kind of early days for them though, so we'll see how high they can go. But these are kind of comparable across technologies and maybe even across vendors. Some of these numbers are a little bit old. And then this, as far as the speed metric goes, this is one where actually there's also a huge difference between vendors, and something important to keep in mind depending on what algorithm or application you're looking to do. If you need to run many executions of the circuit, then the speed starts to become very important. And we can see that there's a 4 orders of magnitude difference between, for example, this trapped ion system from AQT in Innsbruck, and the other vendors here should be similar to this, versus, for example, Google's 2-qubit gate speed, which is 12 nanoseconds. So this is something that's also important to keep in mind when thinking about which system you would like to target. So those are raw numbers of what exists now. I'll quickly flash up kind of roadmaps from the vendors where they are predicting where they think they will be going. Whether this turns out to be true or not is an entirely different story, but this is what the vendors themselves are saying in public, that all 3 of IonQ, Google, and IBM are predicting that they'll have 1,000 physical qubits in either 2023 or 2025, depending on the company. And you can see their predictions. Yeah, I wouldn't take it enormously seriously, but it is kind of interesting to see the trajectory that things have been on so far, that there really has been a fairly rapid increase in the number of qubits that people have been able to develop. And then kind of going forward to sort of 8 years from now, people are predicting that they'll have 1 million physical qubits. I guess we'll see if that comes to be. I think the more interesting question, to me at least, is what improvements in fidelity and connectivity the vendors are going to be able to make. But this is primarily talking about qubit count.
Can I ask a question? I mean, it just seems, based on what you've said so far, that a claim of 1 million physical qubits sounds outlandish. Is it outlandish, or is it? I mean, it doesn't have to be in 2029 exactly, but is it realistic that on that time scale it'll happen?
It seems unlikely to me that will come to pass, but I don't know.
Can I make a comment?
Sure.
They have been very cagey about not promising there'll be good qubits. Okay, they can meet their commitments without doing it with good qubits. They can't do anything useful.
Right. Even with making bad qubits, I think 1 million is really hard though. Unless you go, okay, we're not even going to connect them to wires, and we're not going to put them into a dill fridge. Yeah, I think making a system of 1 million useful qubits, even for very rough definition of useful, seems very, very difficult though, because the amount of wiring complexity, the amount of cooling power you need, all of this looks very, very challenging once you get beyond, let's say, 1,000.
Well, I don't think it's true that they're not making any promises about the fidelity, because on this upper plot from Google, the top right of the screen, they have the physics de-risked thing at is that 10? I need to zoom into your thing to read what that says. That's 10 to the 4 qubits, so 10,000. And they have 1 logical qubit at 1,000 qubits. So they are hoping to be able to implement some kind of error correction code at 1,000 qubits.
They're not committing to having done error correction that improves over physical, though. They could do that with terrible gates. Don't worry. The IBM people are covered. They're going to get they're going to meet their milestones. Hopefully they can do something good too.
Could I
So-
ask how is the all-to-all circuit? How does that function? It's not like it's a non-local operation, like if it's
Sure. So one way one can think about, so there's essentially two ways that works. There's the IonQ way and the Honeywell way. If we're going to give the companies credit for it, they didn't invent it, but you could call it the, yeah. Anyway, there are academic predecessors of this, of course, but the IonQ way is that they have a linear trap of ions and a linear array of ions in a trap, and they use the motional modes essentially as a bus to couple the qubits so that they can each feel each other via the Coulomb repulsion and the motional modes that the motion that results. And the Honeywell way of dealing with this is that you can have a planar chip where you trap ions on the chip and you can physically move the ions around so that ion here can kind of be moved into an interaction zone, interact, and then be taken back.
I see.
And
Thank
that's
you.
very different, of course, than like superconducting circuits where it's defined where each qubit is by lithography in a fabrication process, and then the qubits are fixed in space.
Right.
And the neutral atom people are also starting to explore this notion of being able to move things around because they are trapping their qubits using optical tweezers that can be moved in time. So they may end up having a similar situation to the Honeywell style ion chip traps where you can shuttle things.
That sounds very slow though, right?
Yeah, there's definitely speed limits to it. I saw some recent results from presented by either Vladan Vuletic or Misha Lukin. I can't remember who was showing them, or maybe it was both of them, showing how fast they can go. And essentially, yeah, if they try to go too fast, you end up getting causing extra decoherence. But there's some rate at which they can go, which was fast enough that they could propagate quantum information around a relatively small lattice. How well the technique scales, I guess, is still TBD. Cool. So on from, vendor predictions of the future, which I think we can mostly take with a grain of salt once we go out beyond the next year or two, to give some at least pictures of what I mean by connectivity and the kinds of connectivity that the different vendors are tending to implement at the moment. So we've already shown an example of a Google 2D square lattice. Rigetti and IBM are two other vendors building superconducting circuits, and here are some examples of the kind of lattice geometries that they're implementing. You can see this Rigetti one is kind of quasi 1D, but wouldn't exactly call it 1D, but it's close to 1D. And IBM are building a number of different topologies, but here's an example of one which is kind of like also quasi 1D, but sort of like a ladder. And then IonQ, Honeywell, and AQC, at least at the scales they're at the moment, are all able to do all-to-all connectivity. So this is some sort of representative examples to give you a feel for what's available at the moment or what people have constructed at the moment.
Peter, just out of curiosity, why is it complicated to make sort of two layers, and then you could imagine connected all to all much more easily?
Right. So you can imagine that in superconducting circuits, people could maybe make kind of layered structures where they then get a 3D cubic lattice at least.
Or even just two layers would already, seem like
2D lattice, two layers would.
Just two 2D lattices, just two sheets of 2D lattices.
Right. I think this is in principle possible. It's probably difficult in practice, partially because people are already using the third dimension to bring in all the control lines and the readout resonators and so on. So I think there's the qubits, but then there's all the classical infrastructure around the qubits to be able to control them and read them out. And you're tending to use the other dimensions already for that already. And maybe there's some room to have a few layers and bring some wires down between the qubits or something like this.
Well, you still have two half spaces, right? So you might hope if you're using just a half space that you could do it from both sides. But,
people are like, there's a lot of effort in the superconducting circuit community, especially on kind of constructing devices that use the third dimension, but there's a lot of practical difficulties in the fabrication processes that make it not so easy to just go, okay, well, we want something like this and sandwich it together. It generally tends to take many years of work for each time they want to add a kind of new complication to how they fabricate, at least when they want to scale. All right, so that's connectivity. So now let's go beyond these kind of raw metrics and talk a little bit about some applications people have done, because I think that's maybe the more interesting metric. So one particular example of an application that people like to run on near-term or noisy machines, because it at least works to some extent on noisy machines, is the so-called variational quantum eigensolver, or VQE, which is a variational quantum algorithm for computing, for example, ground state energies of a given Hamiltonian. And if you haven't seen this before, the idea or the concept is very simple. If you have some quantum circuit that has a bunch of parameters that you can tune, and you just fiddle with the parameters, and then after fiddling with the parameters, you measure the energy of the state you got with respect to the Hamiltonian you're trying to find the ground state of, and you just kind of keep fiddling with the parameters until you get a lower and lower energy. And the demonstrations of this that are state of the art to my knowledge for chemistry problems are the ones that are shown here. Google has done a demonstration of a rather artificial molecule, hydrogen 12, using 12 qubits. And with this, they achieved an error in their computed ground state energy of 1 millihartree, where a hartree is a quantum chemist's unit of energy. And lower is better, and an error of less than 1 millihartree is considered by quantum chemists to be the sort of threshold for you're now able to predict chemical properties reasonably accurately. So this is what the quantum chemists target. So this is a very good demonstration, even though it's with a rather artificial molecule, and it's still a rather small number of qubits that we used. IBM has published a result with 6 qubits, simulating beryllium hydride. And there the error was 500 times larger, and in particular 500 times larger than this threshold for what is considered acceptable by chemists. This was a couple of years ago though, so there's kind of a big jump that happened between these two papers. And IonQ's also published a 4 qubit demonstration with water, getting an error down to 4 millihartree. So this is at least encouraging to me in that we're able to get down to good error or good enough errors in the quantum chemistry sense, but it's still using a relatively modest number of qubits. This is still something you can easily simulate on your laptop. So there are interesting demonstrations, but there has not yet been a demonstration of quantum advantage in quantum chemistry with VQE yet. You probably need to get up to somewhere around 40 to 50 qubits before you can hope to and still achieve this error rate before you can hope to say that you did this faster or better than a laptop could have. So besides VQE, here are some other applications that people have been running. These are the kind of the largest ones I know of. Random circuit sampling is, as the name suggests, you run circuits that are with randomly chosen gates, and the entire purpose of this is just to demonstrate so-called quantum computational supremacy, namely that your quantum computer can do anything better than a laptop or even a classical supercomputer. And this was demonstrated by Google a couple of years ago. There's been a subsequent work, essentially a replication essentially by USTC in China with a 60 qubit superconducting processor with a very similar design to the Google one. And this is a rather abstract task, though. It's essentially like the task that the quantum computer most naturally does, and is not particularly useful for anything else. Then in VQE, we've already talked about that on the previous slide. The largest demonstration I know of is for quantum chemistry is 12 qubits. Google also recently put out a paper showing a dynamic simulation where you're not trying to calculate a static property like the ground state energy, but you're trying to observe the dynamics of the system as you evolve a Hamiltonian in time. And this they demonstrated using 16 qubits. There's also an example of demonstration of a quantum optimization algorithm with 23 qubits. And then on a also sort of more abstract, but coming closer to maybe quantum fundamentals or a HEP plus QIS link, a demonstration of scrambling with 53 qubits. So they used all the qubits, working qubits on their chip, also by Google, and a recent demonstration of, it's following a long line of work on time crystals. That's also in this kind of category of implementing quantum dynamics in a somewhat abstract setting with a spin chain of 20 qubits in a 1D line. So something to take away from this is that even though Google arguably has the most sophisticated quantum computing chip that's available at the moment, and it has 53 qubits, in almost all cases where people actually run an application on it, they're only using a very small subset of the qubits, so 12 qubits or 16 qubits or 20 qubits or 23 qubits. The exceptions were random circuit sampling and scrambling. And this is not an accident. It's not because Google didn't want to use more than 12 qubits in their VQE demonstration. Just the machine connectivity, the speed, the fidelity, everything sort of conspired to that's the largest they could get it to work at. So this is the kind of practical scale that we're at the moment, constrained by all the things that are other than the qubit count, the metrics besides the qubit count. So something to kind of note here that kind of connects with this previous slide of the fact that random circuit sampling they did with 53 qubits and scrambling was done with 53 qubits is when you're thinking about an experiment to run on quantum hardware, can you find some application where the noise that the quantum computer has, the decoherence, is either helpful or at least not actively harmful? And this at first glance might seem like a completely ridiculous thing to wonder, but imagine you are trying to do a quantum simulation of some quantum system that is coupled to a bath, and in the setting that you would like to study it in, it is also coupled to a bath, and that bath happens to be similar to the bath that affects the quantum computer you're running on. Then you wanted the decoherence and you got it. So it would be nice to find applications of quantum computers where this is true, where the noise that the machines naturally have maps to the noise you're interested in studying in whatever it is that you're trying to study. Maybe this is too much to hope for, and at best you can hope for finding applications where the noise is at least, if not helpful, at least it's not too bad for you, kind of at least not actively harmful. And an example of this is in SYK model simulations in some sense. So their decoherence is perhaps still a problem, but often in SYK you have a random Hamiltonian, and so if the noise in your quantum computer was your inability to specify the parameters of the Hamiltonian perfectly, if you're doing a simulation of SYK, this may not actually be a problem because you were picking the coefficients randomly anyway. So it's an example of maybe where it's not necessarily desirable, but it's not actively harmful either. And so I think this is something useful to keep in mind when thinking of kind of what are the things we could run on quantum hardware, because we're, for the foreseeable future, going to be constrained by decoherence and circuit depth.
Can I ask a question about this? Is it understood in any of these setups what the noise profile is actually?
Yeah, so people have spent quite a lot of time trying to understand the decoherence mechanisms and properties in the different hardware, and for each of the different vendors and each of the different chips they produce, they will have different noise spectra, different noise characteristics, different noise sources. So it's very much sort of at least vendor to vendor dependent, but even I think within the vendors, we see different behavior on different machines that, for example, IBM produce. But there is a lot of work that's gone into trying to do noise spectroscopy and so on, because people would like to understand what the mechanism is so they can get rid of it. So yeah, lots is understood, although there's also still lots that are just not understood. Of like, where does this error come from? We don't know where, we don't know how. If we did, we'd get rid of it.
No, but for the application you suggested, it would, for many things, it would be sufficient to know what the noise spectrum is from a theoretical point of view. So if that data is known, you could try to incorporate that into some kind of effective model building.
That's right. That's right. And so that's kind of what I'm suggesting is that, yeah, we should think of ones where the noise is part of the model anyway, and that's what you wanted. And yeah, maybe some machines will have an appropriate noise spectrum and some won't. And you should kind of get from the vendor or from doing your own experiments on it, extract the relevant noise parameters. Does it approximately follow just a simple depolarizing channel, or is it actually non-Markovian, etc.? And it'll depend on the application which one you want.
Right. Thanks.
Alban.
How easy would it be to actually design the noise? And I mean, they're not obviously not trying to do that now, but is that something you could actually imagine doing in your time frame?
Sure. So I think something that I've done in experiments in my own work is adding noise, and that's certainly doable. So if you take a system that had no noise, you could always add noise with the desired spectrum. So that's always something that's possible. You could always make noise where there wasn't before. I guess the tricky thing is people have tended to make the machines have kind of as little noise as possible, and then they get to whatever state they get to, and that's as good as it got. And if they knew how to get rid of more of it, they would have done so. And so shaping things so that the noise spectrum is what you want, but also it's at as low an amplitude or intensity as what you already had is, I think you can't have both worlds. You can either add noise and have it be shaped to your desire, or you have the lowest noise possible, but with a spectrum that is just given to you. You don't get to control it. At least that's my kind of view of it. Maybe for some specific systems, you could be smarter and they already know that there's kind of like a no free lunch thing and the noise has to be somewhere, but they could shape it for you. I'm not aware of systems where it's true, but I won't say that they don't exist. It's probably going to be on a experiment by experiment or kind of hardware platform by hardware platform basis.
Okay, good, thanks.
Can I also ask, just to follow up, I mean, in this, you envision the quantum computer really acting like an analog computer, right? You're not performing a calculation that would just simulate the.
Yeah, I certainly think of it in the most natural way. I think of this as in doing some quantum simulation where it's an analog quantum simulator, or you kind of have some model Hamiltonian, you try and make the machine realize that. That's the most natural setting in which I can think of this kind of coming true. But I think it's probably true in the circuit model too, where it's discrete time, but you're doing simulations are still where it most naturally makes sense to me, but I don't think it has to be in the analog setting. I think even in the digital setting where you're doing some trotterized evolution, this could also come into play.
I see. Okay.
Great. So yeah, this brings us to some sort of more HEP plus QIS overlap discussion. And I think the high level question from my perspective, at least as a QIS person who's interested in what could quantum computers possibly help with in the study of high energy physics in general, or quantum gravity as a specific example, is kind of what are the features of gravity that we can capture in a model that only needs, let's say at most 1,000 qubits, but also needs more than 50 qubits. And why do I say this? Because if you have fewer than 50 qubits, but especially let's say fewer than 30 qubits, we can already solve that model exactly on a laptop or maybe a classical workstation. So we wanted to use enough qubits that we couldn't solve it classically, but also we don't want it to use a small enough number that we can imagine running an experiment in the near future, in the, let's say, the next few years. So what is that model that sits in this sort of sweet spot between 50 and 1,000 qubits? And I don't have an answer to that yet, but I think that's an interesting question for this community to explore. As an example of something that I think maybe fits more into the category of it used too few qubits, but nevertheless is a concrete proposal that people have made, is this set of people from Google and Stanford and elsewhere, entitled Quantum Gravity in the Lab. And essentially the proposal in this paper, for those of you who haven't seen it before, is a quantum teleportation circuit that works in a rather weird way, and which is supposedly analogous to a traversable wormhole. So the quantum circuit diagram they draw is this one that's shown here, where it goes time and the circuit operations flow from bottom to top. They propose starting with a thermofield double state. You take half of it, you apply some scrambling unitary, then you inject in a quantum state, psi n, you apply a scrambling unitary again, you then apply a unitary that couples this subsystem on the left with this subsystem on the right, apply another scrambling unitary, and kind of by magic, but also by their construction, this you get a state out, psi out, that under certain conditions is this state psi in. So you performed a teleportation of this state from this kind of left subsystem out to this right subsystem. And this is very different than the conventional teleportation circuit one would typically find in a quantum computing textbook. So it's teleportation, but by a different mechanism that involves these kind of scrambling unitaries. And something that kind of is interesting about this proposal is that it has the scrambling unitary could be, for example, an SYK Hamiltonian evolution. And so it has this perhaps property that it's a little bit more robust to implement on a near-term machine, because you just need random couplings that are fixed. You don't need very precise control over the couplings in your SYK Hamiltonian. That said, I'm not familiar with or not aware of any actual implementation of this protocol yet at any scale on real quantum hardware. So even though this is still a pretty toy model at a pretty small scale and something pretty simple that is pretty well matched to hardware that we have today, it's still not simple to get this to work on machines that exist now. But this is the kind of flavor of thing that I think is working towards something simple enough that we could actually do it on a real machine. But then one naturally asks, okay, well, what could you learn by running it on a real machine that you couldn't have just running it on a laptop? And I don't know whether this particular protocol and proposal has a sense in which if you simulate it with 20 qubits, you will learn something different than if you simulate it with 50 or 100 qubits. I just don't know. It would be interesting if there was. I suspect that there may not be, though, in this particular case. So, yeah, why would you want to try study SYK on a quantum computer? Well, there's kind of this robustness argument, but first of all, why SYK at all? Well, I think for this audience, this is kind of well known, so I'll go through quickly. It's a simple theory that has a gravity jewel. You can construct these analogs of traversable wormholes, as in this protocol that I showed you on the previous slide. It's maximally chaotic at large n, low temperature. So this kind of chaotic behavior, scrambling behavior is interesting. There's also kind of this notion of if you couple it to a bath, you get something joule to JT gravity, coupled to flat space. So that's also kind of interesting connection with potentially being able to simulate wormholes and so on. And why on a quantum computer? Well, partially it's because this seems like a reasonable match for what machines can currently do. Maybe you can learn things that are interesting about, maybe you can verify some of the analytical results that exist for SYK, and to what extent these analytical results really depend on the ensemble averages. But maybe you can also study things that are like SYK that are not so easy to study analytically, but you can study them numerically in a quantum computer. So I don't think these are the absolute best and strongest arguments, but this is kind of what motivates us at the moment. And to actually do it, you need to kind of deal with these challenges. Well, what do you do about the limited number of qubits and circuit depth and connectivity? The number of qubits, fortunately, is not too bad. We can implement probably somewhere between 40 and 100 Majorana fermions with our 20 to 50 qubit systems. You can use variational quantum algorithms to try reduce the circuit depth you need, and you can also try working on compensation of errors, which is something Elliot's worked a lot on. And to deal with the connectivity, you can try and use ansatz that match the connectivity of the hardware, and maybe something like a product spectrum ansatz will work for this and not require us to go too deep. A final thought that I wanted to kind of put up before I end is almost everything I've talked about so far has been in the context of qubits and commercial machines, but I wanted to mention something, at least to this audience, about the possibility of something that doesn't match very well with what's available commercially. And my lab is doing this, but I think many other labs are investigating this kind of line of thinking as well, is maybe we can design specific quantum devices that match particular Hamiltonians, so that you can make an analog quantum simulator that is a sort of bespoke device that does one particular task really well. You can also imagine doing this in the circuit model, making special purpose devices for circuit model, but I think it's most natural to think about it in an analog quantum simulator setting. And you can include both spin, i.e. qubit, or bosonic continuous variable degrees of freedom in these kind of systems, which could be implemented, for example, with superconducting circuits. So if you think of some model where you need spins, but you also need continuous degrees of freedom, I wanted to kind of mention that this is something that's very reasonable to implement practically in experiment, even though it's not something you'll really hear about from the commercial vendors. The commercial vendors are very focused, in general, it's not universally true, but in general, they're very focused on implementing machines with qubits, and they don't talk much about continuous degrees of freedom. But this is something that is absolutely possible to do and is well suited to working with academic collaborators. And an example of this is a device that my lab's building in collaboration with Will Oliver's group at MIT, where we're coupling a qubit to a multi-mode resonator that has many continuous degrees of freedom in it. And this will realize some kind of spin boson Hamiltonian. So a question for this kind of QIS plus HEP community is kind of what are the interesting high energy physics models, if any, that you can imagine realizing with such a sort of simulator that is a hybrid of spins and bosonic modes. So with that, I think my time is up. So I'll leave this up there. I don't know if we're allowed to go slightly over for one or two more questions, but I'm happy to answer anything more if anyone had any further questions. But otherwise, thank you very much for all the questions already and your attention.
Great, yeah, thanks, Peter. Yeah, I think we have a little bit of time for questions if people want to ask them.
I have a question. Peter, with this kind of a novel quantum simulator, what did you design it? What applications did you design it with in mind?
So this particular one, we had a couple of things in mind, at least three. One of them, which is maybe most close to analog quantum simulation, is that in speaking with some of the quantum chemists, the chemists told me they actually have lots of situations where you can model what they're interested in as a spin boson model. It is one spin coupled to a bosonic bath, but they still want control over the bath, so it's not really a bath in the thermodynamic sense. And this maps to electronic degrees of freedom in some molecule that's coupled to some vibrational degrees of freedom, and the phonons are, of course, bosons. So that's the quantum simulation angle. We were also interested in whether you can use a qubit to mediate interactions between the continuous variable modes in the resonator, and in this way make a kind of multiplexed quantum information processing device where you have one resonator that's one physical device, but it could store many continuous variable degrees of freedom, and to what extent we could kind of engineer that into a useful information processor. So that's a kind of more abstract quantum information sciencey task. But one thing we can imagine doing with that, besides performing tomography and seeing kind of how efficiently we can use the qubit to couple the modes and so on, is we can imagine using this to construct some kind of quantum neural network where we have some programmability between the modes using the qubit that mediates this nonlinear interaction between the modes, and see if we can, using gradient descent, sort of train the parameters of the qubit and the couplings it induces to perform some useful machine learning task for us.
Mm-hmm. I wonder if in some distant future, things like this could be built where, lately there have been all of these very interesting papers where you have an SYK model that's supposed to be dual to a black hole. You couple it to a reservoir, and the reservoir eats up the radiation coming from this thing, and then you decode the interior state from the radiation once you gather enough of it. Of course, nothing like that. You can never study anything like that for real in the sky. But I do wonder if there's in some future date, the thing in the middle with the fermions could be built to be like the SYK, and then it feeds into connect to this. This is the reservoir, and then you try to decode. That would be super cool. I mean, far
right,
away.
and I think that there's like super nice models that people have of like a purely qubit version of this kind of thing, and you could implement that on a standard commercial quantum computer. But then if you wanted to do something that was a little closer to probably the true physics of, there was some maybe fermionic or spin degrees of freedom that coupled genuinely to propagating bosons, i.e. photons, just there would be microwave photons, and then capturing those microwave photons and measuring them in addition to measuring the interior. That seems very plausible. I won't say that it's going to be easy to do, but it seems very believable that one could imagine doing that in the future.
Is it okay if I just jump in and say some things about why it's difficult to simulate SYK? Because Peter mentioned SYK as a potential application of quantum computing, but actually SYK is very difficult to simulate on a quantum computer. And so
sure,
okay?
go wild. I guess I forgot to add the caveat. Like, this looks like an interesting one, but it's still really hard. But yeah, Elliot, why don't you go ahead and explain why it's really hard?
Yeah, so there are a bunch of reasons why simulating SYK on a quantum computer is really hard. One obvious thing is that, so you have these all-to-all interactions among n Majorana fermions, and to encode the Majorana fermions on a quantum computer, you have to do a Jordan-Wigner Bravai-Kataev transformation and write them in terms of spin operators. And when you do that, all of the Hamiltonian terms are these really non-local things that act on like they act on a lot of qubits, especially if you make n large. And those terms, if you want to do any trotterized evolution, that's like really hard. It gets like more difficult the like larger your Pauli operator is for each term in the Hamiltonian. And similarly, if you wanted to do some kind of VQE thing, and so where VQE is variational quantum eigensolver, where you're tuning some ansatz parameters to try to get to the ground state, or in similar applications, you might be trying to get to a thermal state. But in either case, you have to measure the Hamiltonian, and measuring these operators that act on many qubits runs you up against readout errors, because I mean, the qubits on the readout errors on the superconducting quantum computers are like 5 to 10% or something. And if you end up having to read out order n qubits and then like find the bit parity of that thing that you've measured, which is wrong if like any one of those measurements is wrong, then that's difficult to do. So you need some sophisticated readout error mitigation in order to be able to do something like that, which is actually something that I'm working on now. Another problem with SYK is that it has order n to the q terms, where you have q point interactions among the Majorana fermions, and normally often we pick q equals 4 because that's the smallest q that is dual to JT gravity. So then you have n to the 4 terms in your Hamiltonian, which is a lot of terms if n is large, and it's a lot more terms than you have in, for example, 1D spin chain, where you have order n terms.
How big does n really have to be for us to find sort of JT-like effects? Sometimes relatively small n is large enough to get to what you knew? Is there
Well,
something-
you want to make n large enough that you can't simulate it on a classical computer. So you already want to make n like 40 or 50 at least. I think there were, so the number of qubits is actually n over 2. So probably you could go up to like 60 fermions on a classical computer at least. So you want to go up significantly higher than that. And that's really difficult to do on a quantum computer right now. It's like much more difficult than simulating a 1D spin chain.
Cool. Or not cool. Sad.
Yeah. And so Peter was mentioning, well, maybe the fact that the coefficients on your Hamiltonian terms are random, maybe that helps you because you're going to take this ensemble average in the end. But there's still some challenges there because, I mean, if you're doing multiple Trotter steps, you should be evolving with the same Hamiltonian for each Trotter step, not a different random one. And also you have like decoherence effects, which you don't have in actual SYK. And also you would want your average over Hamiltonians to match the SYK ensemble and not just like some other random matrix ensemble. So anyway, it's a difficult problem that I don't think we're really close to being able to do interesting things with SYK on quantum computers.
Okay, great. More questions?
Actually, can I ask one about back to these technologies for quantum computing? Is there any sort of hope or attempt to bring more of them together? Maybe along the lines that Vijay was saying, like couple one type of quantum computer to actually another one with different technology?
That's a great question. So there's a lot of interest, at least in academia, on quantum networking, where one of the goals is to try be able to connect multiple quantum computers together, potentially with different kind of physical substrates. I think in the commercial world, people are very focused on just making their one thing the thing that wins. But in the long run, people want to build quantum networks. So people are working on this. For example, there's a bunch of people working on how do you take superconducting circuit qubits, which are essentially storing information in microwave photons. How do you convert those microwave photons to optical photons so that you can propagate them along an optical fiber out of the fridge and either go to another fridge with the superconducting circuit in, or it could go to a trapped ion computer and absorb the photon and transfer the information to the ion. So this is something that kind of there's a sort of vision for this in the quantum networking community, but it's been very challenging to do this sort of transduction between different. You basically you need to somehow get, if you're going to do this, you generally need to get your qubit converted to a photon somehow. And you want to do this with very high fidelity, or as high as possible, because if you turn it into a photon and then the photon gets absorbed, now you've collapsed your state because it should have been entangled with the system, otherwise it wasn't doing anything interesting. So these are things that I think this kind of quantum networking together of different types of machines is probably 10 plus years away, where 10 is probably like a very optimistic estimate. But hybrid systems that are kind of maybe not done by companies, but done by academics are already also things people are actively investigating, or people, for example, working on kind of hybrids between spin qubits and superconducting circuits, where you can imagine using the superconducting resonators to try and mediate interactions between between spin qubits. And this is something that people already work on. So there's definitely kind of a bunch of effort to hybridize things there to where it makes sense. There's somewhere I think it obviously doesn't make sense to try to do it, but when it's making sense, there's generally some group working on it.
Great, thank you.
Okay, any last questions for Peter? Okay, if not, maybe we can thank the speaker again. Thank you very much.
Awesome. Thanks very much,
Virtual.
everyone. Really appreciate it.